Cool.
Great. So thank you to Bill and AI Camp for giving me this opportunity to speak today. That was a great introduction. As Bill said, my presentation is titled End-to-End Data Science Without Leaving the GPU. And without giving away too almost to it. If I notice, I do using CPU RAM, but for the most part, this presentation's title is true. And so here's the agenda of what I want to talk about today, just with some rough timings of what might happen. To be honest, I'm going to try and move through the slides as quick as possible because I want to spend the most time actually doing a live demo using Python code to access MapD, to do visualizations, and then to use XGBoost in order to fit a very simple machine learning model. And so with that, and my job entails helping the user community and occasionally our customers use MapD to its fullest potential. So whether that's showing through blog how to use MapD, doing data engineering work, showing people how MapD integrates with the larger GPU analytics data framework. These are basically my goals. And so along with this webinar is a great opportunity to sort of further that outreach. I'm not a salesman in any way. I think when you see in a little bit, you see my code, you'll quite see the engineer shining through. I'm going to mention this at the end of the talk, but I won't get your contact information. But if you have any professional inquiries, comments, questions about this talk, please feel free to contact me at randy.zwitch@mapd.com. Or if you enjoyed this talk, please tell me on Twitter, tell other people, so maybe that they will watch the video when it comes out. And so to start with the actual content, GPU analytics is starting to consolidate using the Apache Arrow shared memory layout. And the important thing about this is that current data systems frequently look like the left. And so with this example here, these are all open source platforms. You have Spark, Pandas, Impala from Cloudera, Parquet, and so forth. But these could just as easily be Teradata, Tableau, SAS, R, Python for that matter, where each tool frequently has its own binary data format. And what ends up happening in this case is that to pass data between any of these given tools, you end up spending most of your time serializing and deserializing data. You take data from your Teradata instance, you move it over to Looker, perhaps you export from there as a CSV, maybe you import it then into R. All of these operations are very wasteful in terms of time and also focus. The more systems that you have to integrate with, the more issues that you may have with either network connectivity or having trouble, just basic, connecting with the credentials and so on. And so what the Apache Arrow shared memory format is trying to do is to provide a consistent framework for storing data in memory. And when I'm talking about memory, I'm talking about both CPU RAM and GPU RAM. And so as you see with the diagram on the right, if tools buy into the Apache Arrow shared memory layout, they will provide seamless communication between systems with no serialization or deserialization. And without getting too much into the weeds of this, any of you that are familiar with C, C++, or lower level languages, this is literally sharing pointers between the different systems such that they all read out of the same exact memory location. And if you'd like to read more about Apache Arrow, you can go to the link at the bottom here, arrow.apache.org. There's plenty of technical documentation. They explain it in much further depth than is practical here. And so with that, on top of Apache Arrow, we have the GOAI project and the GPU data frame. And so GOAI stands for the GPU Open Analytics Initiative. And this is really an attempt to provide an end-to-end workflow sticking on GPU. GPUs have been growing in popularity in the past 3 or 5 years because so many business problems are parallel in nature. It can be parallelized. For example, if you're doing a query, then you wanted to do a group by statement. Perhaps you wanted to find the average income in the United States. Well, there's 50 United States and several more territories, and you don't need to calculate those in serial. Each person should be allocated to a state, and you can calculate all 50 states in parallel to one another. And so when you're using a CPU that may have 4 or 8 cores, you are limited to the number of computations that you can do, but CPUs are very flexible in what they can do. The flip side of that would be GPUs, which have thousands and thousands of cores and very high GPU bandwidth, but they can do a lot fewer types of operations, and they tend to be more focused on numeric type of processing. And so, again, the goal of this was really to define a common standard and then buy into the shared memory. I have delisted. While I do work at MapD, I'm going to try to avoid making this a salesy presentation, but just to say that MapD does work along with the GOAI initiative. MapD was one of the founding members. But you don't have to start at MapD. You can see my little offshoot here of your data warehouse or data lake. Ultimately, you're not going to get away from having to load data from somewhere. And whether that data is in CSV files, Parquet files, other types of formats, eventually you will have to bring it onto the GPU. And so the question from there is really, after you do that, how do we make our analytics process the most efficient it can be? And so MapD returns results via PyMapD, the Python package, in the GPU data frame format. And with that, we can use tools that have been provided by Continuum Analytics. They are the group that distributes the Anaconda distribution. They've also created Numba, which is a just-in-time compiler that compiles Python code into CUDA kernels. And then as you go further down or further up this diagram, you start to get to model training and inference. And you could have tools such as H2O, which is a machine learning platform, TensorFlow from Google, which a lot of people are familiar with, Torch, and other sorts of machine learning platforms. And in the end, we're hoping that lots of people actually buy into this framework, so that each vendor or tool ends up competing on features and not locking users into binary incompatible formats. And so with that, I'm actually going to move into the demo and show how all this works together. I'm going to check the comments real quick because it appears to be quite a few. Oh, okay, where's everybody coming from? Okay, so there's no comments thus far. The demo and all the code is provided on GitHub. And so if you go to github.com, the MapD account, and then AI Camp, you'll get the Jupyter notebook, which I believe I've saved the results into. You'll also have the requirements file if you want to build your own Conda environment. And then the data set we're going to use is publicly available. It's the New York City taxi data set. I'm not providing that via GitHub, but it is publicly available and quite easy to get. And so with that, I'm actually going to switch over to our Jupyter notebook. And as I said, the first step of getting your data into a GPU data frame is loading it from somewhere. And so in this case, I'm loading the data from MapD and loading some of the other libraries. And so we have PyMapD here. We'll do our connection string. PyMapD is DBI compatible, like most other Python database packages, so it should be very familiar to use. Pandas, XGBoost, and then Matplotlib. And so what we can do is we'll load all of our libraries, connect to MapD, and so just like that, there's nothing that's going to highlight that you're actually connected. Just as a note here, these are the default credentials when you install MapD. This server is actually running on my local, so I don't anticipate having authentication. Hoping that anyone will do that. A connection, we can find out the tables that are listed in MapD. And so in my database instance, we have 7 tables listed. And what we're going to do is we're going to use the table that's called NYC Taxi. And to get the table structure, we can call get table details. And what this will provide are all the columns, all the data types that are provided. And I'm just wrapping this in a Pandas data frame because it will give pretty printing within Jupyter Notebook. And so as I said, this data is publicly available. And it has roughly 1.3 billion taxi trips over a 8-year period. And so we have a lot of data from the type of cab, where exactly people were picked up, at what time, how many passengers there were, and so on. And so we're going to use this data set to build a simple machine learning model to predict the percentage amount somebody will tip after their ride. And so as we scroll through this, I'm going to minimize that a little bit. We can do our data pre-processing. And so for many machine learning frameworks, you need to pre-process your data such that you're passing an array or a two-dimensional array or a matrix to your data. And so what I'm doing here in the pre-processing step is setting a handful of these columns into different groups so that we can process them the same way. And so the prediction column that we're going to use is going to be called, and then all of our feature columns are going to be everything except for the tip amount and the tip percentage. Our numeric variables will be passenger count. We'll have our categorical variables. And then in this case, we have a situation where day of the week and hour are numeric, but at the same time, they are categorical. And so now we can read in our data. These are the handful of columns that I'm going to use, both to make this example easier to access and for brevity. But you will see that I am going to load 5 million taxi trips in. And so when we do that, it will only take but a handful of seconds to load this data into MapD. And then, as I said, because this is in the GPU shared memory format, taxi sample is actually going to represent a pointer to the data on the GPU. We're not streaming the data back to my system. And that's important to keep in mind here, is that as much as possible, the data is not going to transfer from the workstation I'm working on to the laptop I'm presenting on. Okay, so now taxi sample is now available in the GPU memory on my workstation. And again, I'm working separately on a different laptop. And so now we can go back and define our target, which will be tip percentage. So the tip amount divided by the total amount that a person spent on their ride. And again, you'll notice this is instantaneous because we're not doing the calculations per se. Taxi sample tip percentage is going out to the shared memory. It's adding a new reference, but it's not necessarily doing any calculations until we need to use them. And so just to get a feel for the distribution, this is going to be one of the areas where we cheat and we go back to using CPU memory. I'm going to transfer the column of data to my local machine just so that we can plot a histogram using pandas. It is actually possible to do rendering on MapD, but again, I don't want this to be just to talk about MapD, so I want to use tools that everyone's familiar with. And so when we go ahead and import the data into a pandas data frame, we can just do a cumulative histogram. And what we can see here is that roughly 80% of users can tip between 0% and 8% of their total ride. And then as we go up, some people are more, excuse me, more generous, but ultimately tipping tends to be on the low end. This is something that we're going to keep in mind, the number of zeros in this group. It's hard to actually see here, but roughly at the 4% mark, or excuse me, roughly 76 or 78% of people tip nothing. And this is something that's going to cause problems a little later in our model estimation, but we'll talk about that when we get there. And so now we can go to our data pre-processing step. And for the algorithm that I'm going to use, you generally want to do something known as centering your data. And this is where you calculate the mean, and thus you scale your data to values between 0 and 1. And what this allows for is to make the math easier when you're doing the parameter optimization. And so what I have here is just sort of a simple loop that goes through all my numeric variables. So passenger count can be anything from 1 person to potentially, I don't know, 50 people, depending on what counts as a taxi. Trip distance, obviously, is going to be, some distance greater than 0. Temp represents the temperature outside, and then total amount is going to be the amount that's spent on the cab ride. And so we can iterate over these and just fill all of our data, normalize all of our data sets. And so here, again, our numeric processing over 5 million taxi trips has already been completed for all the columns. In this case, because we're actually doing a transformation, the data, the computation was calculated on the GPU and has now modified the columns in place for our taxi sample data set. So now we can go through for categorical variable processing, which our days of week and hour are categories. And so here, this is sort of a weird hack. I learned this from H2O. Because you need the data to be in numbers, but you don't necessarily want to write out all the code to transform every single level. If you do this transformation here of as type, this will change the column type to a NumPy data type. And so if you had something like one of the boroughs, Manhattan, the Bronx, Staten Island, and so forth, it will actually convert those automatically to number levels. And so with that, we can pass that to our one-hot encoding function, which will create a new column for each of the levels in each column. And so it may be hard to understand right here, but taxi sample is being overwritten, and we're taking the original columns, the columns that are past the one-hot encoding, and then we're merging them together. And so what you end up having is a column for each level in the categorical variable, and then we go ahead and we delete the original column because we don't want to store it multiple times. And so again, we go through this, and it happens in relatively quick speed. Okay. And then, so at this point, we've done all the data processing we need, but it may not really be that obvious of what's going on. And so what we can do is the same thing as we did before. We can just do a quick memory transfer. If we take the first 5 records of the data set and then do 2 pandas, we just bring back a tiny amount of data, but it allows us to look at it as if it were on my local machine. And so now you can see where passenger count used to be from 1 to any number of people. You can see now it's been scaled down to values in decimal points. So 1.67, 0.33. And the units in this case don't really matter. If we wanted to at the end, we could go back and rescale the data back to the original values. But ultimately, as I said, this is really just a math issue. It's one of those techniques that you just need to learn and do as you're doing machine learning. And as I said, trip distance, tip amount, total, temperature, all of these variables now are scaled between 0 and 1. Okay, so all of our data is prepared the way that we need it. And so as we go through our, now that we have our data transformed, we can split our data into test and training sets. And that same hack that I was sort of doing before is sort of overkill here. But when we want to create a matrix in the end, we want all the data to have the same exact data type. So some of them are int, some are float, 32 bits, some are 64-bit floats. And so in order to capture all of the data in its original fidelity, we can actually convert everything to 64-bit float, and then that will give us a common data type between all of them. In this row, we're going to use 70% of our records to be part of our training set, and then the remaining 30% will be part of our test data set. And when we run this, you can see we originally had 5 million rows. Our training data set has 3.5 million, and our test data set has 1.5 million. And so at this point, we've done our data prep. We just did some very quick data visualization to understand what our target variable is. And now we're at the last part where we can estimate a model very quickly. And I just want to point out here that for brevity, I'm not going through the entire machine learning workflow, especially all the parameters you could set for XGBoost, and how you would actually optimize all the parameters in this model. Just keep in mind that with any machine learning model, when you have lots and lots of parameters, you're likely to do something like grid search, cross-validation, and other things that are appropriate to tune your parameters. But again, for brevity's sake, I'm not going to cover them here. And so now we're going to move over to XGBoost, which is a GPU and CPU enabled library that was written by some of the folks at H2O. There's other contributors as well, of course. But ultimately, it works fairly well with the GPU data frame. And so the one thing that we have to keep in mind is that XGBoost expects the predicted variable to be the farthest one on the right, and all of the predictor variables to be from the 0th column or the first column to everything except for the rightmost column. So what we can do here is take the training data set and the test data set that we created before, and we can split them up. And what we're going to end up with here is a D matrix, which is the XGBoost format. It's just letting the library know that this data is in the format that it expects. It's really just a thin wrapper around the GPU data frame. And so now we can go ahead and set our parameters. And because tip percentage is a continuous value from anywhere from 0 to infinitely large tip, we're going to use linear regression trees as our XGBoost algorithm. And so we can set that here with parameters. As I said, there are a lot of parameters in XGBoost that you can set, from the number of trees, learning rate, early stopping, and so forth. But we'll go here with the defaults. And the thing to keep in mind here is that when I hit enter on this data is going to process on the GPU and return the results. And if we're lucky, it will be in mere seconds. Okay, so while I was taking a sip of water, this model has already solved itself. And so if you haven't been familiar, or if you haven't done a lot of machine learning in the past, if you think about having a data set of 5 million records, I think we have something like 40 columns, and it's sweeping across the entire data set and building the best optimized model for this given set of parameters. This is solved in less than 10 seconds. And so this is a dramatic change from doing machine learning either on a local laptop or passing it to potentially a large CPU-based cluster. You have all the data transfer. You would have CPU trying to do all the calculations, not necessarily being able to parallelize them all. But again, because we keep this on the GPU, it takes mere seconds. And so why is that important? Well, if you want to actually evaluate lots of different parameters, if you want to search the data space to really get the best model that you can, the faster this runs, the more things that you can try. And so now we're going to find out how good the model actually fits. And as I said, we use the default parameters, so I don't think we're going to get that great of a performance. Okay, and so as you'll see here, in cell 19, we have the explained variance from our model. So we have our predicted values that we get from the predict method. We have what the actual values were for that same data set, so what people actually tipped. And then what we can see is we only explain 16% of the variance in tipping. And so in the real world, maybe that's not so bad. I think we could do a lot better if I spent a lot more time doing grid searching and things of that nature. And perhaps that's a different webinar. But ultimately, we can see how well our model fits here. Like I said, 16% of the variance is explained. But to visualize this, again, we can do a quick data transfer from the GPU to CPU so that I can make a pandas data frame and do the visualization. And so briefly, I'm just taking the predicted results, the actual results, putting them in the same data frame, and doing a similar exercise as before, just creating a cumulative histogram. And what we can see here is this model doesn't work very well at all. For over 80% of the predictions, the predicted tip was too low. And this goes back to what I was talking about before when we examined the cumulative density histogram for our tip percentage. The lower bound of a tip is actually $0. But for a linear regression based framework, nothing stops the straight line from going less than 0 with a predicted tip. And so if we were to use this in a business context, we perhaps could cap the value. If the predicted value is less than 0, we might just cap it at 0. Or we might add more data, do parameter tuning and so forth to try and get a better model. Just for the visual, results. So you can see here, when the predicted value versus the actual value, you actually have a divide by 0 error. And again, were I to actually try and do this for real and put this into production, we would absolutely correct for this type of thing. But you can see here, the actual person for trip 11, they tipped 19.2%. We're only predicting 11% here. Sometimes we're predicting a minus 3% tip, but of course 0 is the lower bound. But hopefully what this has shown is that you can actually do a workflow from end to end of decent size using a GPU. The workstation I'm working on has more than one GPU in it, but the GPU data frame C library does limit you to using one card at the moment. And so I'm using a 1080 Ti card from NVIDIA, which has 11 gigabytes of GPU RAM. And with MapD sort of holding my bigger data set and taking a smaller sample, again, we were able to do 5 million records in nearly instantaneously. And if you had better hardware, you would be able to do bigger data sets or more complex algorithms. And so with that, that's all I have in terms of Python code. I'd like to go back to my presentation and say we definitely have time for questions here at the end. But if you have a private question, a comment about the webinar or the example here, please, again, feel free to contact me at randy.zwitch@mapd.com. You can also find the MapD community. This is more focused on MapD, of course, but we do also have analytics case studies. People post questions about how to do things. And so if you're interested in either case, please either reach out to me via the personal email or drop by our community and leave